Hello, everyone. Welcome to today's session on the crucial aspect of data preprocessing, image preprocessing. This fundamental step is essential to ensure our data is in the right format and quality for training deep learning models. Today, we are going to explore the process using the CFAR10 dataset, a rich collection of 60,000 32 by 32 color images across 10 diverse classes. These classes include objects like cars, airplanes, animals, and more. This dataset is split into 50,000 training images and 10,000 test images. First, let's begin by importing the libraries that we'll need for today's tutorial. We have PyTorch, a powerful deep learning framework. Torch Vision, an extension of PyTorch for handling datasets and transforms. Matplotlib for visualizing our images. NumPy for numerical operations. And PIL, which is Python imaging library for working with images. We proceed by downloading the CFAR10 dataset using Torch Vision's CFAR10 class. We define two datasets, the training dataset and the test dataset, each pointing to its respective subset. By setting the transform equals to none, we indicate that we are not applying any transformation at this point. Next, we'll pick a sample image to display, specifically the 101st image, and store it along with its label. We then use Matplotlib to display the image and print out its label. So we can see that it's a 32 by 32 pixel image. Section 2, data augmentation. Now let's dive into data augmentation, a technique that injects variability into our training dataset. This makes our model more resistant and capable of handling different real-world scenarios. Here are some useful transformations. First, random horizontal flip. This transform horizontally flips the image with a 50% chance, and we can indicate the probability of flipping by input the probability. And this is effective when the orientation of the subject isn't significant for classification, as it diversifies the training data. Second, random crop. The random crop transformation selects a random portion of the image. This simulates varying scales and translations. It's especially valuable when the objects appear at different sizes in your data. Lastly, color jittering. Color jittering introduces controlled changes to the image's color properties. By adjusting brightness, contrast, saturation, and hue, we simulate different lighting conditions. This helps the model become less sensitive to variation in color. Now we can define a series of augmentation transforms using transforms.compose. This function allows us to combine multiple transformations into a single pipeline. We need to transform the images to tensor for further deep learning model training in the last step. We then apply this augmentation pipeline to our training dataset using train dataset.transform equals to train transform. This means that whenever we access an image from the training dataset, these transformations will be automatically applied. Now, we can display one of the image after the transformation. So one thing to note is that when we display the image here, we want to permute the dimensions. This is because after transforming the image object to a tensor object, now the shape of the data is 3 by 32 by 32. However, to display a tensor object, we need the color channels to be in the last dimension. So we want to permute the zeroth dimension to the last dimension. Now this image should have dimension 32 by 32 by 3. And we can see the effect of random crop on this image. Section 3, normalization and standardization. With our augmentation pipeline established, we now move on to normalization and standardization. We first collect pixel values from the entire training dataset and store them in an images array. Next, we calculate the mean and standard deviation of pixel values across each of the RGB channels using NumPy's mean and std functions here. These statistics are crucial for standardizing the pixel values. We then define a normalization transform using transforms.normalize. So this one thing to note is that this transformation is applied after transforming our data to tensor, because we can't use normalization on image objects, and we can only apply it onto tensor objects. So this transformation scales the pixel values so that they have a mean of 0 and a standard deviation of 1 in each channel. We then apply this normalization transform to both the training and test dataset. This ensures that whenever we access an image from this dataset, the pixel values are automatically normalized. And to note, one thing to note is that we only use the mean and standard deviation obtained from the training dataset and apply it to both the train and test dataset, because to prevent data leak, because we would not know the mean and standard deviation of the test dataset. So now we can display the one normalized image. And one thing to know when displaying the normalized image is that since the pixel values are scaled, directly visualizing them might lead to out of range error. As you can see, there's a warning here. This is because the RGB value might no longer be in between 0 to 1. To address this, we have two methods demonstrated as follows. The first method involves using numpy.clip to ensure that pixel values are within a valid range for visualization. This range is typically between 0 and 1. By specifying a minimum and maximum value, we make sure that any values falling outside of this range are clipped to the closest valid value. So here we can see that the warning is gone. And the second method involves reversing the normalization process by unscaling the pixel values. We multiply the normalized image by the standard deviation and then add the mean back. This effectively reverses the scaling, bringing the pixel values back to their original range. This method retains the original contrast and appearance of the image, allowing us to visualize it as we would use with raw pixel values. So we can see that using this method, the image has a less clear contrast compared and less bright compared to the normalized image. To recap, we've covered the initial steps of preparing image data for deep learning. We begin by loading and visualizing the C410 images, following by the implementation of data augmentation techniques to enhance our dataset's diversity. Additionally, we explored normalization, which standardizes the pixel values, contributing to smoother and more effective training.